The IPCC didn't overestimate climate change, nature underreacting to our models. Trump's misleading victory lap over IPCC climate models. Recent climate modeling research published in Geoscientific Model Development has led some scientists to reduce the likelihood of the most extreme emissions pathway historically known as RCP 8.5%. That scenario assumed extraordinarily high future fossil fuel consumption, combined with limited climate policy and continued acceleration of greenhouse gas emissions throughout the century. The reassessment was driven largely by rapid global expansion of renewable energy, falling solar and battery costs, improvements in energy efficiency, and policy shifts away from coal in many regions of the world. In other words, scientists adjusted probabilities because humanity has partially changed course, not because the underlying physics of climate change were wrong. Nevertheless, Donald Trump responded on Truth Social with a political victory lap, claiming good riddance. After 15 years of Democrats promising that climate change is going to destroy the planet, the United Nations Top Climate Committee just admitted that its own projections were wrong. That interpretation fundamentally misrepresents how climate modeling works. The Intergovernmental Panel on Climate Change did not admit climate science was wrong. Climate scenarios are not fixed predictions. They are conditional pathways based on different assumptions about future human behavior, energy use, economics, technology, and policy decisions. RCP 8.5 represented a high emission scenario, effectively a warning about what could happen if fossil fuel dependence continued largely unchecked. As renewable energy deployment accelerated globally, many scientists concluded that this exact pathway had become less likely than previously assumed. Ironically, the very reason some researchers now view RCP 8.5 as less probable is because governments, markets, engineers, and scientists took climate risks seriously enough to begin shifting energy systems away from coal and other high-emission fuels. More importantly, reducing the probability of the most extreme emissions pathway does not mean climate risks have disappeared. In many respects, observed climate impacts are still occurring near, and in some cases beyond, the upper range of earlier projections. Several major climate feedback loops are now intensifying faster than many historical models fully captured, including weakening land carbon sinks, accelerating boreal wildfires, thawing permafrost, declining forest resilience, climate-driven ozone damage to plants, and rapid shifts in atmospheric circulation patterns. Natural systems that once absorbed large amounts of carbon are increasingly becoming unstable or even turning into net carbon sources. This means the debate is no longer simply about direct human emissions alone. The growing concern is that Earth's own feedback mechanisms may increasingly amplify warming independent of future fossil fuel reductions. In that context, claiming that the IPCC was wrong because one high-end emissions pathway became less likely is deeply misleading. The climate system itself may now be evolving in ways that are more nonlinear, more unstable, and potentially more dangerous than many earlier public narratives assumed. The issue was never whether climate models predicted one exact future with certainty. The issue was whether humanity would reduce emissions quickly enough to avoid triggering self-reinforcing climate feedback loops. That question remains very much unresolved. Why less likely does not mean impossible. Reducing the probability of the most extreme fossil fuel emissions pathway does not mean worst-case climate outcomes are no longer possible. One of the greatest challenges in climate science is forecasting the behavior of complex feedback loops operating across Earth's atmosphere, oceans, forests, soils, and cryosphere. Many earlier climate scenarios focused primarily on direct human greenhouse gas emissions. However, a growing body of research now shows that climate-driven feedback mechanisms are already contributing substantial additional greenhouse gas releases, in some cases faster than previously anticipated. Robust and escalating scientific evidence confirms that climate feedback loops are actively weakening natural land carbon sinks while simultaneously injecting additional CO2 into the atmosphere. Among the most concerning developments are accelerating boreal wildfires, forest dieback, drought-driven ecosystem collapse, thawing permafrost, smoldering peatland zombie fires, weakening soil carbon storage, and declining plant productivity from ozone pollution and heat stress. Historically, forests, wetlands, and soils absorbed a large fraction of human carbon emissions each year. Increasingly, however, these systems are becoming less efficient at carbon uptake, and in some regions are beginning to reverse into net carbon sources. Permafrost thaw represents a particularly serious long-term risk. Vast northern soils contain enormous quantities of ancient frozen organic matter accumulated over thousands of years. As these regions warm, microbial decomposition accelerates, releasing both carbon dioxide and methane, a greenhouse gas far more potent than CO2 over shorter timescales. At the same time, zombie fires are becoming more common in Arctic and boreal regions. These underground peat fires can continue smoldering for months beneath snow-covered landscapes, releasing ancient carbon stores while also generating methane, black carbon, and ozone-forming pollutants. Surface-level ozone itself is another increasingly important feedback mechanism. Produced during heat waves and stagnant atmospheric conditions, ozone damages plant tissues and suppresses photosynthesis, reducing the biosphere's ability to remove carbon from the atmosphere. In effect, warming can weaken the very ecosystems that previously slowed atmospheric carbon accumulation. This creates a dangerous nonlinear dynamic. More warming, more feedback emissions, weaker carbon sinks, even more warming. Wixen. Climate systems do not always respond gradually. Once critical thresholds are crossed, feedback loops can accelerate change in ways that are difficult to forecast precisely using traditional linear assumptions. For this reason, the declining probability of one specific emission scenario does not guarantee a safer climate trajectory. Even if direct human fossil fuel emissions peak earlier than expected, strengthening natural feedback loops could still push parts of the Earth system toward outcomes resembling higher-end warming pathways. In other words, the greatest uncertainty may no longer be whether humans emit enough carbon to create severe warming, but whether the planet itself begins adding substantially more greenhouse gases on top of human emissions through self-reinforcing climate processes. 2024, a milestone year for climate feedback loops. Q. Is there evidence that climate feedback loops are beginning to add substantial greenhouse gas emissions through mechanisms such as wildfires, zombie fires, climate whiplash, brown carbon, forest dieback, and ozone-driven reductions in plant productivity? A. Yes, a rapidly growing body of scientific evidence indicates that climate feedback loops are already weakening Earth's natural carbon sinks while adding significant additional greenhouse gases to the atmosphere. 2024 became the hottest year ever recorded globally, and the climate system responded accordingly. During recent years marked by extreme heat, drought, wildfire activity, and atmospheric instability, atmospheric CO2 concentrations increased at exceptionally rapid rates even during periods when fossil fuel emission growth remained relatively modest. This divergence is critically important. It suggests that ecosystems previously capable of absorbing large quantities of carbon are losing efficiency, and in some cases beginning to reverse into net carbon sources. Recent global monitoring data indicates that heterotrophic respiration, carbon released through soil decomposition and microbial activity, is increasingly outpacing the amount of carbon plants remove through photosynthesis during major climate anomalies. In effect, parts of the biosphere are beginning to breathe out more carbon than they absorb. Researchers observed a major weakening of the global land carbon sink during 2024, particularly across tropical savannas, grasslands, boreal forests, and drought-stressed ecosystems exposed to prolonged heat extremes. At the same time, multiple reinforcing feedback mechanisms intensified simultaneously. Extreme wildfires released massive pulses of CO2, methane, and brown carbon aerosols. Boreal and Arctic zombie fires continued smoldering underground through winter peat soils, releasing ancient stored carbon. Thawing permafrost accelerated microbial decomposition and methane release. Ozone pollution and heat stress damaged plant tissues and reduced photosynthetic productivity. Forest dieback, insect outbreaks, and drought stress weakened ecosystem resilience across multiple continents. Climate whiplash, rapid swings between severe drought and intense rainfall, destabilized ecosystem carbon cycling. Brown carbon and soot deposition also accelerated Arctic ice and glacier melt by reducing surface reflectivity, further amplifying warming and permafrost thaw. Taken together, these processes reveal a climate system becoming increasingly self-reinforcing. Wildfires, drought, ecosystem collapse, ozone pollution, thawing permafrost, altered atmospheric circulation, and weakening biosphere productivity are no longer isolated environmental events. They are interacting components of a rapidly destabilizing Earth system. The growing concern among researchers is that feedback-driven emissions may increasingly supplement direct human emissions, making future warming trajectories harder to control even if fossil fuel emissions begin to stabilize or decline